Alright guys, welcome back. This is part 3 of example 1 for a 3-moment equation problem. We've already solved the problem in part 2. Basically the question was, if we go back up to the top, it was up here, it was use the 3-moment equation to draw the shear force diagram, bending moment diagram, and solve for the reactions of this problem. So what we did is we used the steps of the 3-moment equation, and we found the internal moments, and then we used those to find the internal shears at each end of the spans, basically doing free body diagrams of each span, virtually like isolated from its reactions, and then from there we basically used all that information to plot a shear force diagram, and then from the shear force diagram we made our bending moment diagram. There is one other way to do this, which I did briefly mention in the there's a video that I made just kind of introducing the concept about the 3-moment equation. And what it suggests is that we kind of do it by parts, or we like add 2 different graphs. So what we want to do actually is we want to grab this one right in here, and let's bring that down where we got some space down here. And then if we just plot on the moments that we had calculated pretty early on, actually, up at this step before we did video 2. So we had MA is negative 100 kilonewton meters, MC is 0, and MB is negative 84.375. So if we come back down, it was MA negative 100, and then MB was at this point, and so that was negative 84.375, and then MC was 0. And then all we have to do is we also knew that the moment at the very free end of this beam was 0, so you just connect these. And this has to do with the principle of superposition talked about in that sort of first explainer video. But the actual bending moment diagram, so basically what we found, oh no, we have it right here. But the actual bending moment diagram, this guy here, is just going to be the superposition of these 2 graphs added together. So basically this blue line added to this green line. Now it's pretty easy to do in the first section because these are all triangles. So if we want to draw, we'll set up the diagram right below. So this first region clearly is just whatever the green line is equal to, because we're not adding it to anything, so it comes down to negative 100. Let's give ourselves just a tiny bit more space to work with here. So this will be the actual BMD. We're going to match basically what we have here, but by adding these 2 graphs, and I'll show you that it's the same thing. So this is negative 100. Maybe I'll just add on some markers too so we know what the distances were. You can kind of see what was left over from here. So this was 5 meters, this was 5 meters, this length was 5 meters, and this length to the peak, well, to the peak of this was 5 meters, but to the peak of the actual bending moment diagram was not 5 meters. So we're going to hold off on that one for a second. But we know that there's going to be some point of interest somewhere in there as well. Okay, so adding straight lines is pretty easy. What we want to do is we want to find out this distance here, this height is 125 kilonewton meters, and then this height, basically we need to take this little section in here, which is 7.8215, because it's just it's just halfway along this triangle, and it's just half the distance, the difference between these 2 values. And we want to add it to this height, which is 84.375, to get this total height in here, or this negative value that I'm going to draw on in pink, which is 92.1875. All right, so if we have 125 minus 92.1875, then the actual like superposition or addition of these 2 graphs or lines, whatever you want to say, that's going to be equal to 32.8125. And that's exactly what we were looking for at this value. And we know, because we're adding these 2 straight lines, that we can just connect these with a straight line. And so this is going to bump up to this value here of 32.8125. All right, the next point of interest is easy for us because we know that the summation of these 2, just 0 plus negative 84.375, is just negative 84.375. So that comes down to that value, and it was somewhere down there. And that, again, we're matching exactly what we did over here. So this is 84.375, right? Just the addition of these 2 numbers. And we're getting the same bending moment diagram, but we didn't actually draw the shear force diagram first like we did in the previous video. So Up until now, it's been pretty easy and honestly, it's really fast if you're just dealing with point loads to be able to get the bending moment diagram. But when we're adding in now in this region, adding parabolas to linear sections. So for this section, really, this is where it really gets messy. What you can do is you can define a coordinate axis starting right here, and we'll be able to plot a simple function for a parabola that peaks out at 125 and opens downwards. Its expression is this. This is basically this is the only way to draw a parabola that opens downwards, has its vertex at 5 units over from the origin and 125 units up, and passes through the origin. And we can actually expand this out and simplify a little bit just to be negative 5x squared plus 50x. All right, we can do the same thing here. We can write an expression for this line. Basically, just do y is equal to mx plus b, and so we get y. Let's call this y2. Its slope is going to be well, it rises 84 units over 100 units, so this is 8.4375x. Plus b, so it's plus its y-intercept, which is minus, if this was the origin, then this would be its y-intercept, so minus 84.375. And now what we have to do is just add every single value for like every value of x, basically. And the way that you do that is the resulting function that we're going to get, I'm just going to call it y_bmd, right? This is just like the y values on the bending moment diagram. And it's in this region, it's just equal to y1 plus y2. So that's just going to be equal to negative 5x squared plus 58 minus 84. All right, so that would actually describe the function, and we could plot it numerically if we wanted to. But the faster thing that we're usually after is just the location of the maximum. So what you do is you take the derivative, you just go y prime of bmd, and that's just going to be equal to negative 10x plus 58.4375, and you set that equal to 0, because where that's equal to 0 you get your local maximum. So if you just rearrange for x from this, you just get x is equal to 5.84375. That's basically the distance from here. You go 5 units over, 5.84 units over. That's the location of the maximum. And then what you can do is you can plug that back into y_bmd. So if you plug in 5.84375 into all of these x's, then we get y is equal to 86.372. 86.372 at x equals 5.84375. Like units away from where we started here at this origin that we set up. So when we compare that to what we got when we did this the other way, we're saying that the distance was 5.84 out and 86 units up. And oops, where'd we go? There we are. And that's exactly what we had. We have 5.84375 units. This is the distance from the maximum, or distance from this point over to the maximum. And then its magnitude is 86.372. So that's kind of cool. It just shows you that adding up these two different curves at every point gives you the exact same bending moment diagram as if we had done it the other way, where first we separated everything out and did the shear force diagram. Just this way, I think is harder and takes longer. So I would totally recommend doing it the other way. I just wanted to show you guys that this way is possible too. All right, so we got it drawn on there. We can, if you want to keep going, you can also generate the shear force diagram from the bending moment diagram. It's a little bit backwards to probably what you're used to, but we can do that by just working backwards a little bit. So we know that where we have a linear change in the bending moment diagram, that has to be a horizontal section on the shear force diagram. And actually we should label this as the shear force diagram. And where it's going negative, that means that area has to be negative. So 100, so basically we have a rectangle, its base times height is equal to 100, negative 100. So we have, we know the base is 5, so the height has to be 20. When we look at the bending moment diagram from this region, it's we're getting an increase, a change in magnitude of 132, basically 100 plus 32.8. So that means that we have a positive area. It's a straight line, so it's a linear change. So we have a horizontal line on the bending moment diagram, or on the shear force diagram. So basically you take that magnitude, base times height equals that change. So this change divided by the base, which is 5, gives you the height. So 132.8125 divided by 5 gives you 26.5625. All right, and you can look at it this other way. So now 26.5625 times 5 gives you that change in magnitude. So if you were to work this way, it probably makes more sense for you. I think it's definitely harder to go from bending moment diagrams to shear force diagrams. But anyways, in this region we have negative change in magnitude. The change in magnitude is 32.8 plus 84.3. So that's going to be a total change in magnitude of 117.1875. If you divide that by the distance that we're going over, so basically we're doing like the reverse of base times height. So we divide the total divided by the base. It's going to give us the height, which is negative 23.4375. And I just realized that I drew this little purple marker in the wrong spot. It should be right here where the parabola starts. Yeah. Alright, so this last part is the trickiest part of it, but if we look at the change in magnitude from this point until the max, we get 84.375 plus 86.372. That change in magnitude is equal to 170.747, okay? And this change in magnitude goes towards the positive direction as we go from left to right. So this area on the shear force diagram has to be positive. And because it's parabolic, I know that this has to be a linear change, basically giving us a triangular area. So this is going to be is equal to 1/2 times the base, which is 5.84375, right? Because we're only going until this point, because after this point, we start getting negative change in area, so the area will become negative, times the height, which is our kind of unknown value right now. So if we just rearrange this and solve for h, we're going to find that h, the height of the triangular area that we're dealing with in the shear force diagram, is going to be 58.437. All right, so we can come in and we can draw that. It's going to be up somewhere about here. And then because I know that this is one single distributed load, we can do all sorts of things. We can just drop it by 10 kilonewtons per meter if we want, because that's what the original distributed load was. We can just connect it through this dot because we know it has to go through there. There's a few different ways you can interpret that. And then as for finding out what this height here is, same thing. We can do similar triangles if we want, or we could recognize that the change in this area here has to equal this change in magnitude. So that would be like to be 41.562. So either way, however you want to do it, that's what we find this value to be. All right, and then the problem was to draw the shear force diagram and the bending moment diagram. We've actually done both of those. We just did them in reverse order this time. And then the other thing would be to find for the reactions. So AY is going to be this jump here. It's just 20 plus 26.5625. That's 46.5625 kilonewtons. The jump is up as we go left to right, so that that force is oriented upwards. This jump going down is due to the point loop. Let's see if we can find a diagram. Where was that? Yeah, there we go. So this is a 50 kilonewton point load pressing down. That's what that jump is coming from. And then this next jump here is going to be from the reaction at B. So this is going to be BY. And we have 23.4375 plus 58.437. That gives us a magnitude of 81.8745 kilonewtons. That's going up. And then when we look here, same as the last video. Actually, this is all the same as the last video, but we have negative shear here, so it's going down like that, opposite the positive sign convention. So of at a magnitude of 41. Then we have 41 going up for the reaction. So CY is just equal to 41.562 kilonewtons, the same as that shear basically, but it's positive, kilonewtons going up. All right, and then if you add these up again, you'll find that these equal 170 kilonewtons all pressing up. All the applied forces pressing down were equal to 170, same as what we discovered in the last video. And you can even compare it there, 46, 81, and 41. 46, 81, and 41. So there you go. That's just another way to solve these problems. It's kind of doing an opposite, more graphically, if you will, but also I think just way more confusing and way slower really than doing it the other method. But just in case you were curious, about when you've seen people stacking graphs like that, that's basically the method down here that we can also use when we're doing the 3-moment equation to solve for the reactions and the two diagrams.